So we're looking at graphing on the logarithmic scale. So we've made some tables. We're going to plot points to see our graphs. So here, I want you to graph all of them on the standard scale or linear scale. It's linear because if you look at the graph marks, it's the same space to get from, we're looking at going from here to there. It's the same space. They're counted by ones on the graph. So go ahead and plot your points and sketch each of those graphs on the standard axis. Okay, so we have the graphs. What are the only graphs that appear linear on the standard scale, on the linear axes? Which of these graphs are linear? Alex?
The graph A of x equals x.
Right, the graph of a of x equals x. Only graphs of the first degree are linear on the standard scale. So only linear graphs x to the first power appear as lines on a linear scale. And again, it's called linear scale because each tick mark stands for a standard amount. It's a set amount. You're adding to get from one number to the next, basically, on the grid. The other ones don't. We've graphed these before. We've plotted points. The first way you learn how to graph things is to plot points. So going back. So now if you look at, now we have graph paper. We're not going to graph all of them, but I want you to find the one that's logarithmic on the y-axis. And linear on the x-axis. So your x-axis is still counting. How are we getting from one number, one big line mark to the next on here? What are we actually doing on the y-axis? How do you get from 10 to the first to 10 squared? What do you do to 10 to the first to get 10 squared? What do you do to 10 to the 0 to get 10 to the first? You multiply by 10, which lets you add a power. So now on your x-axis, you're actually multiplying. Okay, so the best way to look at plotting these points is to write what these numbers represent. So 10 to the 0 is what? 1. Okay, 10 to the 0. 10 to the first is 10. 10 squared is 100. 10 to the negative 1 would be a tenth. And 10 to the negative 2 would be 100. So now I'm looking at these in between here. Are those marks equally spaced? No, they're definitely not equal spaced, but they still stand for, you're going from 1 to 10 with 10 spaces in between. What do you think each of those marks in there represent then? You're going from 1 to 10 with 10 spaces. Yeah, they all stand for 1. So this is actually the number 2. This is the number 3 there. There would be 4. There would be 5, and so on. And so now if we're looking at the next one, to go from 10 to 100 with 10 spaces, what does each space represent? And now it's representing tens. So here's 20s there. This would be 30. There's 40, and so on. Okay, so it's using this different way of counting where you're multiplying on your y scale. Similarly here, we're going from a tenth to 1. So 10 to 1, so this would be 2 tenths, 3 tenths, 4 tenths, so on. And then here, 100 to a tenth. So here we have 2 hundredths, then 300ths, 400ths, so on. Okay, so we still have a graph, it's just a different way of numbering it. So if I was going to graph the x cubed, b of x equals x cubed over c is blue, so I find -2, -8. Where's -8 at on here? Where's -8 on the y scale? There isn't, right? Where's 0 on the y scale? There isn't, okay. So you're not going to be able to plot all the points on the logarithms. Not on our y scale, so we can't plot those, but we can plot 1, 1. Okay, so find 1, 1. And we could plot 2, 8, 2, 8, so let's see. Here's 10, so 2, 8. If we extended this, we would get 3, and what 3 cubed is? 27, right? So we could, now we can plot 327 on our graph. So 3, there's 20, here's 30, I know it's in between there. So I'm just going to estimate here, this is b of x equals x cubed. So it's not as easy to plot that x cubed. Let's look at the 10 dx. Next we did 10 dx. We have -2 under x, so I find -2 and 100. Okay, -2, 100. -1, a tenth. 0, 1. 1, 10. 2, 100. So here's our c of x equals 10 to the x power. And similarly, if we did the 2 to the x, so we have -2 and a quarter, so let's see, there's 2 tenths, there's 3 tenths. I know it's somewhere in between -1, well here's -1, 2 tenths, 3 tenths, 4 tenths, 5 tenths, 0, 1, 1, 2, so let's see, here's 1, there's 2, 2, 4, there was 1, so 2, so there was 2, so there's 3, 4. So there's our fx equals 2 to the x power. What do you notice about those graphs? What do they look like to you? Yeah, they look like they're linear. If you graph an exponential function on a graph where the y-axis is logarithmic and the x-axis is linear, it'll appear to be like a line. It's because of scaling involved. Here, you're multiplying to get from one grid mark to the next, correct? Well, exponential functions, you multiply to get from one output to the next, basically. So exponential functions appear linear on logarithmic Does it make sense how to graph these? I mean, it's a different coordinate system, or a different way of numbering the coordinate system, but it's still the idea. You figure out where your points are, you plot the points, you connect the dots, it gives you a good idea